All right, let me just minimize this. Okay, so as I mentioned in the introduction, we've started taking a different approach to the Summer Institute. We know that there are a lot of you here um, who are essentially users of our advanced cyber infrastructure rather than programmers. But I think this is a topic that everybody can really benefit from. Doing a little bit of introduction to some of the key parallel computing, some of the key parallel computing concepts. I have a few examples in my GitHub repo. You don't need to remember this. The content's also been copied into the Summer Institute repo. So as I mentioned, I'm the Director of Education and Training here at the Supercomputer Center, physicist by training, but more of a computational science generalist. Yep, so for our agenda for this session, we're going to start off with an introduction. We're then going to go into processes and threads and MPI and OpenMP. We're going to talk about hybrid applications that involve a combination of processes and threads. This is becoming a really important topic now that our nodes are getting fatter and fatter. In that sense, I mean more hardware with the node, more memory, more compute cores. We're going to talk about Amdahl's law. If you learn just one of the fundamentals of parallel computing, I'm going to say that Amdahl's law is probably the most important. We're going to talk about other limits on the scalability of applications. We'll then cover running parallel applications and doing a scaling study. And then finally, where to go next to get some more information. Okay, so I realized I had edited this for a different presentation. So ignore all of the references to machine learning. This is actually much more general. So the reason that most of you are here is that you have applications that have grown to the point where you can no longer run them on your local resources. Our laptops or desktops, they're so powerful that you can really do a lot with them, but eventually you may outgrow them and you need to start using parallel computers. And that's what we do here. Our big systems, for the last 25 years have essentially been constructed from multiple compute nodes that are networked together to work as a supercomputer. We realized we could only squeeze so much power out of a particular CPU. Even if you don't go beyond running on a single compute node, you're probably going to be using multiple cores on that node. So like I said, I had edited this presentation and then I forgot to edit it back. But the concepts I talk about a little bit in the context of machine learning, but it's going to apply to any parallel computing workload. So this session is intended for anyone who currently runs or is planning to run or is even thinking about running parallel applications and parallel computers. So for this audience, I'm going to assume it's pretty much everybody who's here. If you write proposals for computer time on your campus cluster or on nationally allocated systems like Expanse or other resources, if you purchase time and compute resources and want to maximize the return on investment, again, this could be a time on a system at an HPC center, or it could be in the cloud. If you have any role in purchasing hardware for your lab, or if you are simply curious about parallel computing, which again, I think is going to span everybody who's in this session. So the motivation for kicking things off with these parallel computing concepts is we find that much of the training in parallel computing is targeted at people who write their own parallel applications. And it really focuses on the programmer topics that you're going to see later in this week: MPI and OpenMP and CUDA and profile and performance tuning. So as a consequence, those of you who are end users, who are not really developers, you rarely or never get a proper introduction to parallel computing. So even if you don't write code, again, like many of you using somebody else's application, it's still important to understand some of these basic principles of parallel computing so that you can make the most effective use of valuable advanced cyber infrastructure. So we're talking about improving your own research productivity, but also making sure that we as a center get the most, I would put, the most science done per cycle. So there are a few myths of parallel computing. Again, for this audience, I hope that most of you are already aware that these are myths, but I'd encourage you to spread the word to your colleagues, to your lab mates, others you work with at your home institutions. So for a very, very long time, there was this myth that parallel computing was for, for areas like astrophysics and engineering and climate modeling and others who are working in these traditionally math-intensive fields. Pretty much, fields where you're solving systems of partial differential equations. So this might have been partially true decades ago. When I first came to the center back in 1997, our user base was relatively narrow. But nowadays, pretty much every field of research makes use of parallel computing. And we're finding more and more uptake from the social sciences, the life sciences. In fact, fields like molecular biology and plant and animal genomics and biomedical research. Those researchers actually use more than half of the time on our supercomputers. We see some from the arts and the humanities, but of course the traditional users of HPC, physics and chemistry and engineering and material science, they're still around. But the main takeaway is that parallel computing is pretty much for everybody now who has large computational needs. Another myth that we see, and how would I put it? Would affect both your own productivity and the effective use of our HPC systems, is that throwing more hardware at a problem is going to automatically reduce the time to solution. It's surprising the number of new users who will get on a system like Expanse or Stampede or Bridges 2 or these other national resources. And they have a serial application, but they'll run it on multiple cores. And what happens is the same application is going to be running independently, often with the same input data on each of those cores. So parallel computing is only going to help if you have an application that's already been written to take advantage of that parallel hardware. And even if you do have a parallel code, and this is something we're going to talk about quite a bit, a little bit later on, is that there's going to be an inherent limit on the scalability. And there are multiple factors that affect how much hardware you'll be able to use to reduce your time to solution. The one caveat I want to mention, and I kind of alluded to this already, is what we call high throughput computing, where you can use parallel computing to run many single core or single GPU instances of an application to achieve near perfect scaling. In fact, if you have that kind of a workload where each of the computations could be done independently, we strongly encourage you to use this high throughput computing model, because there's how would I put it? That will essentially give you 100% scalability. Most of our workloads though are not high throughput computing. And then finally, the third myth we find for parallel computing is that you need to be a programmer or software developer to make use of parallel computing. And as many of you know, especially those of you who are just attending the first 2 days of this week, most users of parallel computers are not programmers. Instead, they use mature third-party software that's been developed elsewhere and made available to the community. And to me, this is one of the one of the best trends in scientific computing that I've seen in the last couple of decades, where back in the 80s or the 90s, pretty much everybody was on their own. There were a handful of mature applications out there developed by groups that really specialize in creating these applications. But nowadays there's so much mature software that you don't need to write your chemistry or your molecular dynamics or your climate modeling application. These are really, in many cases, really big applications that required large teams of developers. So again, there's all those all the software resources available to you, and you don't need to be a programmer or developer to use them. So to kind of summarize, many of you are going to be using somebody else's code. So I'm showing examples here on the left of weather modeling using WRF, molecular dynamics using molecular dynamics of biological systems, using Amber and GROMACS and NAMD and other applications. On the bottom here, the construction of phylogenetic trees. I would say this is one of the big success stories in the last decade. At the Supercomputer Center, we have a science gateway that allows users to upload genomic data and construct these phylogenetic trees. So we've made parallel computing available to an entire community of ecologists and environmental scientists who otherwise would need to, well, I'm going to say not develop their own applications, but would have to really figure out how to run these applications on their own. And again, supported by that community of developers in phylogenetics. And also, example here of electronic structure calculations using something called CP2K. Okay, a little bit about parallel computers. I think you got an introduction to this on Wednesday, so I'm going to go through this pretty quickly. But modern clusters and parallel computers really they're comprised of multiple compute nodes that are networked together using a very fast interconnect. It could be something like 100 gigabit Ethernet. So you're probably all familiar with Ethernet. This kind of takes it up to the next level in terms of bandwidth. Most of the machines that we've had in recent years use something called InfiniBand. You don't really need to worry about the details, except that InfiniBand gives you, depending on the generation of InfiniBand that you're using, equal or better bandwidth to the latest versions of Ethernet, but also very, very low latency. And I'm going to say this is what really makes a parallel computer, that interconnect between the nodes. Each of those CPU nodes typically contains two multi-core processors. In our case with Expanse, you have two 64-core processors for a total of 128 cores. And the GPU nodes normally contain 4 GPUs. So if we want to effectively use this hardware, we need to have applications been parallelized that they can run across the multiple cores or the GPUs within a node or across nodes. Okay, so moving on to the next topic, we're going to discuss processes, threads, MPI, and OpenMP. Let's make a note here. Okay, so you might have heard of these terms in the past, processes and threads. You could think of both of these as ways to implement parallelization. Threads and processes are both independent sequences of execution, but there's an important difference between the two of them. You could think of a process as being an instance of a program. So these processes, each of them will have their own pool of memory. They're going to have what they call preserved state. They can open and close files. They have access to file descriptors. So again, just think of a process as an instance of a program. When we get to MPI, when we get to talking about MPI, keep in mind that a application that's been parallelized using MPI is really just running multiple instances of that program, each one a process, and then moving data between those processes. A thread is something a little more lightweight that executes inside of a process. So every process is going to have at least one thread, so you kind of get one thread by default, and you can have multiple threads within a process, and they can all access shared memory. So there are some great online resources describing the difference between threads and processes. Only problem is that they tend to be geared more toward computer scientists rather than computational scientists like yourself. But I'm going to say that the following two resources do a pretty good job of addressing the topic. So I found a really good thread on Stack Overflow But as you might expect, if you're familiar with Stack Overflow, it's a little deeper, a little nerdier. But there's also um, another great description that I found, a little more informal at, I'm not sure how you pronounce it, educba.com. Talks about process versus thread. So I'm going to say maybe take a look at at that second link first if you want to dig deeper, and then if you want to go deeper, dig deeper still, you can go to Stack Overflow. Okay, a few more distinctions between process and threads. Processes, they are heavyweight. They incur a little more overhead, but they're also more flexible than threads. Multiple processes, they can be run within a compute node, or you can have processes across multiple compute nodes, taking advantage of what we call distributed memory, and then explicitly communicating data over the network between those processes using something like MPI. Threads incur less overhead, they're much lighter weight. Threaded codes can use less memory, since the threads within a process have access to that same data structure. If you stick around for the entire week, you'll see a session that covers OpenMP and MPI and talks a little bit more about threads and processes. But threads are also less flexible. Multiple threads associated with the process can only be run within a compute node. So within a node where they have access to that shared memory. Okay, so we talked about process and threads. We're going to get to the I think the key point now, and that is, why do I care about process and threads, especially if I am not developing my own software? So the type of parallelization is going to determine how and where you're going to run your code. So for distributed memory applications, this is the multiple processes or multiple instances of a program. This can be run on one or more nodes. Shared memory or threaded applications should only be run on a single node. If you try to run on more than one node, you are going to get absolutely no additional benefits. Hybrid applications, so this is a combination of threads and processes, can be run on one or more nodes, but you should consider the balance between threads and processes in order to get the best performance. And in all cases, you may need to consider how processes and threads are mapped and bound to cores. So in addition, just being aware of threads and processes will help you to understand how your code is utilizing the hardware and sometimes identify common problems. So I said up front that this is not a session for programmers. This is a topic for end users. But I do want to talk just a little bit about message passing interface, or MPI, and OpenMP. You're going to hear these discussed. You don't need to program in them if you're not developing applications, but you should at least be aware of what they are. So MPI is what we call the de facto standard for parallelizing C, C++, and Fortran codes to run on distributed memory, multiple compute node systems. So this surprised me sometimes. It is not an official standard, but it has become the de facto standard, meaning that pretty much everybody uses it. So it's back in the days when MPI was first developed, there were a few competing standards. Remember, there's something called PVM. I forget what else, which I don't believe any of those are supported anymore. So MPI was kind of the survivor, which you'll see used very, very extensively. So there are multiple open source implementations of MPI. So you may hear terms like OpenMPI or MVAPITCH or MVAPITCH2 or MPITCH. And then vendors like Intel can also, support their own versions of MPI. What's important though is that these are just implementations of the MPI standard. Within maybe some of the cutting edge features in the newer releases of MPI, where say all of the very, very newest developments haven't been implemented everywhere. Other than that though, OpenMPI, MVAPITCH, MPITCH, they all give you the same interface to MPI. So you do not need to rewrite your applications in order to use one or the other. Now, what we do find though is that certain applications will run faster, or get better scaling using a particular implementation. MPI applications, they can be run within a single shared memory node. So all widely used MPI implementations, they are optimized to take advantage of the faster intranode communications. Mentioned already that MPI is portable. It can be used. It can be used pretty much anywhere. And then, although MPI is often synonymous with distributed memory parallelization, there are other options out there. There's a system called Charm++, which is really gaining a lot of interest. It is the it is used, in NAMD, one of the most widely used molecular dynamic applications. There's something called UPC X10. So even though you think of MPI as being synonymous with distributed memory parallelization, there are other options out there, and some of which give you a little bit more flexibility than MPI. Okay, so although we've been discussing MPI, the same principles are going to apply when parallelizing deep learning applications. Again, this is a slide that was left over from our Machine Learning Institute, but there's something called Horovod. This is a distributed deep learning training framework for TensorFlow, Keras, PyTorch, Apache, MXNet. There's also Nickel, which is the NVIDIA collective communication library. And this is used for multi-GPU and multi-node communications. So I'm going to show you a small fragment of an MPI application. Again, if you are not a programmer or an application developer, you do not need to know MPI, but I just want you to be aware that it exists, and let's get a peek at what it looks like. So when you started programming, whether it was C, C++, Java, Python, you probably wrote some variation of a hello world. In this case, this is a snippet of C code. In our main program, we have one statement, print hello world. Now, if we wanted to parallelize this so that each process writes the hello world, it would now look like this, where all of the new content needed to parallelize is shown in purple and bold. So in this case, we had to include a header to get access to the MPI function prototypes and constants. We needed to initialize environment, get the number of processors, get the rank of the process. So when we have an MPI application, when we start off, the only thing that distinguishes the individual instances of the program or the processes is what they call the rank, numbered 0 through n, n minus 1, where n is the total number of processes. We can get the name of the processor, and then finally down here we have each process saying hello world and telling us what their node name is and the rank out of how many processes. And then finally, we need to finalize the MPI environment. So you can see that an MPI application can become a little more complicated, a little bit harder to read. This case is a little extreme since we had to do all of the parallel, all of the MPI overhead of declaring processes, rank, and so on. In a real application, you're going to find that the ratio of code, of original serial code to the additional code added for parallelization is fairly small. Okay, OpenMP is another application programming interface, or API, and this is for shared memory within a node. And currently, OpenMP is available for C, C++, and Fortran. It provides a collection of compiler directives, library routines, and environment variables. Unlike MPI, which is the library, OpenMP is supported by the compiler. And to date, I have not seen a major compiler, including IBM, Intel, GCC, that's the GNU Piler collection, PGI, the AMD optimizing compilers, that does not support OpenMP. Again, OpenMP is portable. So once we have a code that's been parallelized with OpenMP, we can run it on any system. And like MPI, OpenMP is often taken to be synonymous with shared memory parallelization. But there are other other options. There's a language out there called Silk, which is essentially C with a few minor extensions, POSIX threads, and specialized libraries for Python, R, and other programming languages. To show you what an OpenMP example would look like, I'm going to say the same thing that I did for MPI. If you are not a programmer or an application developer, you do not need to know OpenMP, but you do need to know that it exists. This is going to be particularly important if you are building your executable. Let's say you get somebody else's code and you need to compile it. There are certain flags that you'll need to use depending on which compiler. It might be -f OpenMP, -q OpenMP, or -mp. And this is all recorded in the expense user guide. And in fact, you'll probably see this described in the user guides for all of the major supercomputer centers. So here's a simple case. Again, if you're not a programmer, you can kind of ignore what we're doing. But if you have a little bit of programming experience, see here we have a main program. We're going to initialize 3 arrays, A, B, and C. We're going to assign them some values, and then we're going to add those arrays element by element. So this is what the code would look like if we parallelize it using OpenMP. We start off by adding a header so that we have have access to the constants and runtime library. We defined a chunk size here, which sets how large the unit of work is that's going to be assigned to each of the threads. And then the construct that you're going to see most often in a code parallelized using OpenMP is one of these pragmas, where we say which variables or arrays are shared. We're doing a static scheduling where we're taking chunks of work and handing them to each thread. And then once they're done, they can go back and get their next chunk. So what we've done is we've taken this loop and we parallelized it so that those iterations could be spread across multiple cores. Like I said, if you're not a programmer, you don't need to know OpenMP, but you do need to be aware it exists. And for your parallel application, you want to know if it's been parallelized, to use processes, to use threads, or to use the combination of both. So the big picture, for MPI and OpenMP, on the left-hand side, we show OpenMP, where multiple processes are managed using MPI. And then MPI is implemented in libraries, such as mpitch or mvapitch or mvapitch2 and OpenMPI and vendor implementations. Threads, multiple threads are managed using OpenMP, and then OpenMP is implemented by the compilers. And that could be the GCC, Intel, AOCC, PGI, or others. And with that, I realized I've been talking for quite a while. Are there any questions before I move on?
No questions at this time, Bob.
Okay, great. Thanks, Cindy. So if you do have any questions, feel free to chime in as we go along. We have folks on our side who are going to be monitoring the Slack. All right, so I'm going to talk next about hybrid applications. So many modern parallel applications are built using a hybrid approach to take advantage of both distributed and shared memory. And typically this is going to involve some combination of MPI and OpenMP, although other combinations are possible. We talked about other approaches to parallelism beside MPI and OpenMP. But generally your hybrid application is going to be this mix of MPI and OpenMP. The reason we do this is over the years, these nodes have become, say, fatter and fatter. We now have 128 cores in each of our compute nodes. And we find that, say, building just straight MPI applications are a little more efficient when you were working within a node. So hybrid codes have this advantage over purely shared or purely distributed memory applications. So a shared memory application can have limited scalability within a node, but it cannot be run at all across multiple nodes. So if it's a shared memory app, say parallelized using IP, you are stuck to running within that node. Distributed memory applications, you might think this is going to be a little more general because I could run, say, an MPI application within a node or across nodes. But these distributed memory apps, they may have higher memory requirements. They may have more overhead when running within a node. So if we're really concerned with performance, we may find that's just more efficient to run using a combination of these two approaches, distributed and shared memory parallelization. So we're going to strip things down, talk about a very, very simplified parallel computer. In this case, our parallel computer consists of just 2 compute nodes, each with 16 cores, and they're joined by a network. So on the left, we show one of the nodes. Think of that large box shaded gray as being a node, and those little blue boxes as being the compute cores within a node. And these are 2 identical nodes, again connected by that interconnect. So if we have a message passing application, we would, and let's say it's just purely message passing, say parallelized using MPI. We typically we could execute 1 process per core. And I'm going to say this is the old style, where we're running just a straight MPI application. In this case, we're running 32 processes across 16 cores. The orange box indicates a process. So we have 1 process associated with each of those cores. If we have a straight threaded application, again, parallelized using OpenMP, we're going to be restricted to running within a single node. And this example shows a threaded application, single process, running 16 threads on 16 cores. So here the large orange box, again, is 1 process, and it's spanning all of those cores. Now I have a caveat on the bottom of the slide. Technically, any programming model can be mapped to any hardware, but in practice, threaded applications are always run within a single node for best performance. About 8 years ago, we had a system where we're working with some experimental software that would allow you to run threaded applications across multiple nodes, across distributed memory. So again, although it could be done, it was terribly inefficient, and we really didn't find any use cases where it was valuable. Now, hybrid applications, and this is what you're going to be seeing more and more often, is a combination of threads and processes. So here's an example, going back to our 2-node system, each with the 16 cores, where we're running 4 processes, 2 processes on each node, and then 8 threads within the process. So on the node on the left, we have those 2 processes, each running on 8 cores. And then when we need to do the message passing across nodes, we will go over this network. A typical scenario is to run 1 process per node, using threads within that node, and then message passing across nodes. But we're seeing, though, that this is becoming a little less common as the number of cores on a node continues to grow. And this is where things get a little tricky. When we have a hybrid application, we can, and we want to run across multiple nodes, we could do everything from the situation here on the left, where we have 1 process per node, and then however many cores we have within that node, that number of threads, all the way over to the other extreme, which would be like running a straight MPI application, where we have 1 process per core, but in reality, the sweet spot is going to be somewhere in between. So in the case of our 16 core nodes, anywhere from 1 process per node with 16 threads per process down to using straight MPI, or somewhere in between, say like this middle case where it's 4 processes per node times 4 cores per process. Main thing is that you want the number of the processes times the number of cores per process on each node to add up, to the product to equal the number of cores. All right, before we go on, any questions about hybrid applications? All right, well, I will continue then. So we're going to shift gears a little bit, talk about the theory going behind parallel computing. So I'm sure many of you have already heard Amdahl's law, that this is the fundamental law that describes the absolute limit on the speed up that your code can get as a function of the proportion of the code that can be parallelized and the number of processors. If you know just one law of parallel computing, this is the one to know. This is the most fundamental law of parallel computing. So let's let P be the fraction of the code that can be parallelized. So work that can be, that could be divided up, shared across multiple processes or threads, and let S be the fraction of the code that must be run sequentially. And of course, the S plus P is going to have to equal to 1, and N be the number of processors. So again, this is very theoretical, very high level. We're not getting into whether or not a piece of code could be parallelized, but rather just the what fraction work can be run in parallel. So the speed up as a function of the number of processors is going to be 1 over 1 minus P plus P over N. And as the number of processors goes to infinity, the theoretical speedup is going to depend only on the proportion of the parallel content. So let's look at Amdahl's law again. We'll let n go to infinity, and we could see that this term here, the second half of the denominator, P over N, that's going to vanish. We take that parallel content, we keep throwing more and more hardware at it until it takes a negligible amount of time, and then we're going to be left with that serial content. So the serial content could be I/O. It could be a bottleneck where we need to collect data from across all processes and threads and do some sort of parallelization. Regardless, it's that content that we cannot take and divide and subdivide and spread across multiple processes. So when you look at Amdahl's law, you say that doesn't look too bad. Let's say I just have a little bit of serial content. I should be able to get really good speed up, but we're going to see in the next slide that it only takes a little bit of serial content to really limit your ability to scale out on a parallel machine. So I'm showing a plot here. I have code for this in the GitHub repo. Again, both in the URL that I had on the opening slide and in the GitHub repo for the Summer Institute. So what we're showing here is the speed up that you get for your code as a function of the number of cores. And we did this for different degrees of parallel content. So let's say that half of the work could be parallelized. The maximum speed up that we're going to get, regardless of how many cores we run on, is going to be 2. And if we have 75% parallel content, maximum speed up is going to be 4, 90% max speed up of 10, 95% max speed up of 20. This is a good time to add that you can't look at your code and say, know outright how much parallel content it's going to have. You can kind of estimate this by doing benchmarking, at different core counts. But a little hard to exactly pin down. But the big takeaway here is that it doesn't take much serial content to limit your scalability, to severely limit your scalability. So I added one more data point on this next slide, and that is having 99% parallel content. And even with 99% of the content being able to be parallelized, the maximum speed up we're going to be able to get is a factor of 100. So this is the same plot that we had on the previous slide, except with one more curve. And note that you need to be aware of not just the maximum speed up, but the speed up that you're getting at lower core counts. So here we have this code. I think that's the upper curve in the teal color. Even with a code with 99% parallelizable content, even there, we would make terrible use of a full 128 core node. So in this case, we're running on 128 cores. We would only get a speed up of a little under 60x. So that's actually a terrible use of that node. We should be running the application further down in the curve using maybe 64 or even 32 cores. Okay, any questions before I move on? Okay, if not, just have a few more topics before we wrap up. And we're going to be now discussing other limits in scalability. So Amdahl's law, this sets a theoretical upper limit on speed up, but there are other factors that are going to affect your scalability. There's going to be communications overhead. How long does it take to move data between processes across that network between nodes? There's going to be limits set by the problem size. You know, if our problem's not large enough, we just don't have enough units of work to spread it across, say, thousands or tens of thousands of processes. You know, a good example I see online in Introduction to Parallel Computing is, say, painting a fence, where let's say we have a 40-foot length of fence. We get one person painting. You know, let's say they could accomplish a job in 10 hours. We get two people on there. They can kind of work independently in each half of their fence. They could, you know, cut the runtime in half. But eventually, we get to the point where you can only get so many people on that fence. Maybe you could get a 2x speed up with 2 painters, a 4x speed up with 4 painters. But on a 40-foot wide section of fence, you can't put 100 people or 1,000 people. You just don't have a large enough problem to divide up the work that finely. There's also the issue of uneven load balancing. And then, so real-life applications that involve communications, synchronization, you know, where threads or processes must complete their work before everybody can proceed, irregular problems, non-Cartesian grids. All of these factors mean that your speed up can be much less than what's predicted by Amdahl's law. So in terms of load balancing, parallelizing a code requires dividing the computational work that can be executed independently. But if the work cannot be distributed evenly, then processors will sit idle waiting for the longest chunk to finish. So here I'm showing a case with running an application on 4 CPUs. Same thing would apply if we're running on GPUs or if we're running on more than 4. The blue bar, the blue chunks, indicate when that CPU is busy, and the red and white hatched chunks are when that process is idle. So let's say we start off, we have chunks of work that we assign to CPUs 0, 1, 2, and 3. CPU 2 has that largest chunk of work. Oh, and we're also going to assume that there are synchronization points where all of the tasks must complete their processing. Let's say because they need to exchange newly computed results, or threads need to finish updating a shared array. We're going to assume that there are these synchronization points that nobody can go past until all of the processes or threads have finished. So in this case, CPU 2 got the largest chunk of work, and it's going to sit, and it's going to be waiting until CPU 0, 1, and 3 finish their work. In fact, if we if we could say run a movie of this, we'd see that CPU 2 finishes first, followed by CPU 0. So now they're both sitting idle, waiting for 1 and 3. Then 3 finishes, and then finally 1. Now we can synchronize. Now we go on to the next step. We distribute the work again. Again, it's uneven, and we may find that that processes or threads have to wait. So this is going to affect your scalability. In fact, I had worked in an application about 10 years ago that took this to an extreme, where the chunks of work varied anywhere from from well under a second to multiple minutes. So we had to do some um, some clever implementation of parallelization to take that work and achieve a better load balancing. There's also communications overhead. So this is going to apply especially to those of you who are solving systems of partial differential equations. So if you're doing, say, CFD or magnetohydrodynamics or climate or weather, or any of these other types of simulations that involve solving PDEs on a grid, this is going to be a very common situation. So let's say that and this is an unrealistically small problem, but let's say that we're working on a 16 by 16 grid, and we could divide this into 4 8 by 8 chunks, and we're going to distribute them across processes. So processes 0, 1, 2, and 3, each of them is going to get a chunk of that problem, say an 8 by 8 chunk out of that 16 by 16 grid. And when we're solving these systems of PDEs, typically we need to get access to values, say for temperatures, pressure, salinity, chemical composition in all of the neighboring cells. So for cells that are within the interior of each chunk, calculations can be done within a process. So I've highlighted one red cell in each of these 4 chunks, and you can see that the neighbors that you need are all contained within their chunk. But for cells at the boundaries, they are going to need data belonging to neighboring processes. So to accommodate this, the code is going to be written to put a halo of what they call ghost cells around the chunk. And now we need to communicate data between processes. And here the data movement is going to depend on both the latency and the bandwidth of the network. And this is going to introduce communications overheads. So before we update the values of the cells around the edge of each chunk, we're going to need to exchange columns or rows of data, like we've shown here. Oops, sorry. Yeah, so we're going to need to exchange entire columns and rows of data. So the let's look at the top row. This column of cells in dark blue is going to have to be communicated to the neighboring process, and it's going to fill a column of the ghost cells. Similarly with the rows and the other processes. Again, don't need to get into the details, but you just need to be aware that there is going to be this communications overhead. So by now, you're probably thinking, how does anybody ever really use a parallel computer effectively? We already have that hard limit imposed by Amdahl's law. And again, that's just a theoretical upper limit. That doesn't say anything about, doesn't take into account load balancing or communications overhead, or any of the other factors that come into play with the parallelization of your algorithm. So how does anybody ever use all the cores on a single modern compute node, let alone the full power of a large supercomputer? So the reality, first of all, is that most parallel applications do not scale to thousands or even hundreds of cores. You're often going to be running within a node or on a small number of nodes. But there are still applications that do scale to these thousands of cores. So they have a couple of strategies to handle this. First of all, they'll often grow the problem size with the number of cores or nodes. So rather than trying to solve a fixed size problem using more and more cores, they'll go out and they'll solve a larger problem. So going back to the fence analogy, you might not, how I would put it, you wouldn't hire a thousand people to paint a 40-foot section of fence, but you might hire 1,000 people to paint a mile-long stretch of fence. So you start working on larger problems. You'll see this a lot in climate and weather simulations. Instead of using, say, a particular grid size, they'll use a much finer grid. Now they have a larger problem that could map onto a larger supercomputer. You can overlap communications with computation. So for example, you could have communications going on at the same time that you're also doing useful work. You could do dynamic load balancing to assign work to cores as they become idle. And you can also increase the ratio of the computation to communications. So if we were doing, if we have a CFD application, those computational flow dynamics, they scale well, but eventually they'll run out of steam because you're doing, relatively large amount of communications compared to the amount of work within those cells. But if we do something like reactive flow, where we actually need to solve the chemistry within each of those cells, we've now increased the ratio of that computation to the communications. Okay, so have one more topic before we wrap up, and this is going to be on running parallel applications and doing scaling studies. So when we run a parallel application, so far we've covered the basics of parallel computing. We talked about hardware and threads and processes and hybrid applications and how we implement parallelization, say using MPI and OpenMP and Amdahl's law and other factors that affect scalability. So all this theory and background is great, but how do we know how many CPUs or GPUs to use when we're running our parallel application? Say, let's go back to Amdahl's law. It's nice that we have this fundamental law that tells us what speedup we get as a function of the parallel or serial content. But it's very hard to look at your application and figure out what the values are going to be for P and S. So the only way to definitively answer this question, how many cores, CPUs, GPUs should I be running on, is to perform what we call a scaling study. And we need to do this with a representative problem that's run on different number of processors. And when we say representative, we mean one with the same size, say grid dimensions, number of particles, images, genomes, and complexity, the level of theory for computational chemistry calculation, the type of analysis, the physics that we include, the approximations that we make. So this representative problem has to look like the research problems that you want to solve. So we see this a lot in applications for computer time, where we will get a scaling curve showing runtime as a function of the number of cores. What we're doing here is something called strong scaling. We have a fixed size problem that we run on increasingly large number of cores. Believe it or not, these are these codes have very, very different scaling behavior. But when I present it like this, when I show it on linear scale, on linear axes, time versus cores, they look indistinguishable. But if we do this the right way, and we plot the results on log axes, this gives us a lot more insight. So we have log axis for time, log axis for the number of cores. And we can see that on the left, that this is a code that has perfect scalability. I'm showing here in red that the runtime is a function of number of cores. Get a straight line. I've included this black bar as a guide to show you what linear scaling would be. So it's entirely possible that this red line is going to be linear, but it would have a different slope. So it would be shallower than linear scaling. Another thing that you might find useful is if you include the parallel efficiency on the right axis. So parallel efficiency is just a measure of your speed up relative to the number of cores. For example, if I run on 64 cores and it's 64 times faster, that gives us a parallel efficiency of 100%. Now on the right, and this is indeed the same data that we had in the previous slide, where the left and right plots are indistinguishable. On the right, now we see that we start off with pretty good parallel efficiency. If we plot the, we're getting good scaling. We're pretty close to linear at small core counts. Parallel efficiency is up here at close to 90%, and eventually it drops off. So where should I be on the scaling curve? So if your work is not particularly sensitive to the time to complete a single run, consider using CPU or GPU counts that are close or very close to 100% efficiency, even if that means running multiple instances on a single core. And this is going to make a lot of sense if you have parameter sweep workloads, say where if you're a computational chemist or a molecular biologist, and you need to do the same kind of calculation many times. I'm going to say run out here on these small core counts. Try to keep your parallel efficiency over 80%. Now, sometimes it's okay to go a little bit further out on the scaling curve. So if the time to solution for that particular task is important, or if it would just take an unreasonably long time at lower core counts, in that case, you may want to run at a little bit lower parallel efficiency, but you should have a good justification for this. You would definitely want to do this if your code does not have checkpoint restart capabilities. That means that you can write out the state of the system. This is very common for climate and weather codes and computational fluid dynamics, where you can, after a particular time step, you write out the data so that you could then read that in later and restart. But if you don't have those checkpoint restart capabilities, and the runtime would exceed the queue or the partition limits, then you'll have no choice except to run at a little bit higher core counts. Sometimes it's okay to run at even poorer parallel efficiency, and that's if time to solution is absolutely critical. So let's say that you're doing calculations that need to be run on a regular schedule. Say data is collected every day during the day, and we need to process this overnight. A good example is the use of our previous supercomputer, Comet, which we now operate for the Scripps Institution of Oceanography. They use that during the rainy season to do atmospheric river simulations of atmospheric rivers based on recent satellite data, and they use that to make a prediction of rainfall throughout the West. So that's a case where it's really critical that we process that data each day, and they may run at a lower parallel efficiency because it's just important that they get it done. Or in the extreme case, if we need really, really quick turnaround, we don't use our systems for these kind of essential operational tasks, but say tornado or tsunami predictions. In that case, it is so important that we get that solution as quickly as possible that we should just keep using more and more cores as long as the runtime doesn't increase as we use more cores. Some other considerations, I'll just kind of run over this very quickly. Sometimes you'll need to use more cores in order to get more memory. On Expanse, we have 2 gigabytes of memory per core, but let's say that you just have a very large memory footprint. You would already be charged for those cores, so you might as well use them. You're going to be getting a little bit poorer scaling, but you could justify using more cores to get more memory. So with that, I'm going to wrap things up and hopefully take a few questions. We've really just scratched the surface of parallel computing, but I think you got access to the key points. There are many other training resources, though. If you go to exceed.org, and this is going to be no longer active soon, but Access, the follow-on program to Exceed, will have their own training pages eventually. We have a lot of materials here on the SCSC website. If you are using the nationally allocated systems, Expanse and Bridges 2 and Stampede and others, each of those will have their own user guides, and they're also being tracked through the Exceed portal with the resource monitor. Again, Exceed is going away very soon, but Access will be picking up these duties. So in conclusion, parallel computing is for everyone who has a problem that they need to solve that doesn't fit on their local resources. You generally don't need to be a programmer, but you do need to know the fundamentals in order to effectively use the parallel computers. We talked about processes and threads. Just remember that a process is an instance of a program. A thread is run within a process and access shared data. And MPI and OpenMP are the most commonly used approaches to parallelizing codes. talked about Amdahl's law. It gives you that upper limit in scalability, but there are other factors that affect scalability, such as load imbalance and communications overhead. And finally, know how to display your scaling data and choose core counts. When we see applications for computer time, this is often the weakest part of the proposal. So, to display your scaling data, using log axes, provide tables that we know what your efficiency is at each core count, and give us a strong justification for why you are choosing to run each of the calculations on that number of cores stated. And that is it. And just one final reminder that I have code that was used to generate these figures in my GitHub repo and in the institute, the Summer Institute repo. And in fact, you could use my notebooks to generate the scaling curves for your own data. And with that, I'm going to conclude, and we have, I think, just a couple minutes for questions.